Hi, everybody. My name is John Handler. I'm a principal solutions architect with Amazon Elasticsearch Service. And today we are going to talk about a new feature in Amazon Elasticsearch Service called cross-cluster search. This launched in about June. It is live now, and anybody can use it. What is cross-cluster search? Well, we're going to go into some details about Elasticsearch and Amazon Elasticsearch Service and what it is, but high level, Elasticsearch is delivered to you is a distributed search engine. So we're going to send in our data to Elasticsearch. We're going to send search queries. Perhaps we're going to use it for analytics on top of log data. But all of that is contained in a single cluster. With cross-cluster search, you can actually connect two different clusters to one another to enable you to query across those clusters and send queries from a source to a destination so that you can have essentially a single pane of glass on top of all of your Elasticsearch service infrastructure. And we're going to go into details about this today. We're going to talk about Elasticsearch. We'll talk a little bit about the tenancy situation that generally gives rise to the need for cross-cluster search. And we're going to do a short demo just to look at the setup and a little bit of how it works. Digging into Amazon Elasticsearch Service and Elasticsearch itself, Elasticsearch launched about 10 years ago as a search engine, distributed search engine. And the idea here is that for cases where you have some catalog of data, things like e-commerce where you have a product catalog, or perhaps it's a data lake where you have a large collection of textual data, or perhaps it's application data, some kind of geo-based search data. All of that you would take and format as search documents, which you put into Elasticsearch. And then Elasticsearch will provide you with relevant search results for textual kinds of queries. We're all very familiar with searching. We do this all the time. And Elasticsearch is an example of an open source technology that provides this search functionality for your application and your data. Now, as Elasticsearch was out there and as it sort of grew in popularity, people began to send their log data to Elasticsearch. So log data is sort of interesting in the sense that we have voluminous amounts of log data generated in many different locations in our infrastructure and our applications and our sort of security infrastructure layer. All of that data is large, and when things go wrong, it can be very difficult to figure out what's going on if you have to one by one inspect all of your logs. And of course, with the prevalence of search, people really were used to looking for a search box to dig in and figure out what was going on. So they started flowing their log data into Elasticsearch. Elasticsearch then, the ecosystem grew a couple of technologies. One of them was Logstash. Logstash is streaming ETL over your log data. It picks up your log files line by line, formats each line as JSON, and then sends it off to Elasticsearch. On the other end, we have a technology called Kibana. Kibana sends Elasticsearch queries in order to build visualizations on top of the data in your log files. These are the two main use cases for Amazon Elasticsearch Service and indeed Elasticsearch itself. As we dig in, we'll look at some of the different characteristics and capabilities of these two workloads that require segmentation or separation of the data, and that cross-cluster search would now support. Elasticsearch itself, very easy to use. It sits in the databases world. The interaction model is pretty straightforward. It's all REST-based and JSON APIs. When we're using it for log analytics, you're going to send your log data from your servers, lots of different ways to do that, off to Elasticsearch. It has to be transformed into JSON and sent to Elasticsearch. For search workloads, generally your data will reside in some kind of relational store or maybe a NoSQL store, and that would serve as the source of truth. You would walk any tables in there that you want to index for searching. and send that data again to Elasticsearch via REST API. In Elasticsearch, all of the data is indexed. Every field in that JSON is available as a target for searching. This is one of the differentiators with respect to other database technologies. Elasticsearch, all about indexing. On the outbound side, again, you use REST APIs. You send queries to Elasticsearch. Elasticsearch processes those queries and returns to you either search results or perhaps aggregations and analytics kind of data, which you would either visualize with Kibana or examine yourself. Amazon Elasticsearch Service launched in 2015. Elasticsearch itself can be a little bit difficult to scale, a little bit difficult to operate, and we felt that a managed service would make it easy to deploy, operate, scale Elasticsearch in the AWS cloud. So Amazon Elasticsearch Service delivers that to you. We're going to examine just a few of the basics of Elasticsearch. When you use Elasticsearch, as I mentioned, it is a distributed search engine. We have a number of different components of Elasticsearch, and it's important to understand how they work. When you use Amazon Elasticsearch Service, you create what we call a domain. A domain wraps a set of hardware and software within a service-owned and managed VPC. This is service-owned hardware and software in a service-owned VPC, and it presents to you an endpoint, which is a DNS name where you can interact and send your REST commands. That DNS name points to a load balancer that balances the requests across a set of nodes that are called data nodes. Data nodes, pretty uncomplicated, hold the data, respond to indexing requests, and respond to search queries. You deploy your data nodes based on the scale of your mostly data, but also processing needs. And in the service, you simply specify how many nodes you want, and we go and give them to you. We also support a node type, which is the ultra-warm node. Ultra-warm is a feature for log analytics that enables you to store a long tail, a much longer time frame of log data at a much reduced cost point, based on our using S3 as a backing store for those nodes. You trade off a little bit in latency, but you can save up to 90% on storage, and the cost can be, much reduced. Finally, we have master nodes. Master nodes are orchestrators. They hold the cluster state. They keep the cluster functioning as a cluster. So all of that software and hardware then comes to you across that REST endpoint. We have a number of different security features. You can use IAM to restrict access to the endpoint of the cluster. You can use the OpenDistro security plugin for fine-grained access control. And in this way, you can secure all of the data in your cluster. We also have some inbound and outbound connections and integrations. We send data, metrics about how the cluster is performing to Amazon CloudWatch. And we also send audit type information to AWS CloudTrail that gives you the means of knowing who's doing administrative actions on your cluster. On the inbound side, we support connections from Amazon Kinesis Data Firehose, and we support AWS Database Migration Service, as well as sources for logs or for, obviously, search use cases. We also have integration with Amazon CloudWatch logs through the console that makes it straightforward to forward data from CloudWatch logs to Amazon Elasticsearch Service. Within Elasticsearch, when you send your data in, you're going to store it in an index. An index is actually a high-level conceptual construct that organizes the data within your domain. You can compare it with a database table. It's not a perfect analogy, but it's close enough. When you're using Amazon Elasticsearch Service for log analytics, you're going to stream in your data, and generally the life cycle is to manage that data by day. That's the usual use case. So you're going to manage it by time frame, creating one index per time period. And again, usually the time period there is a day. So within Elasticsearch, I'm going to have a number of indexes corresponding to how long I want to retain the data in my Elasticsearch service domain. This would be a 7-day retention window. I'm flowing in logs from today, if today is November 26, 2018. I have additional data from the 25th, 24th, 23rd, 22nd, et cetera. All of that data is generally passive. For log analytics, today's index is usually the most active index. When I'm using Amazon Elasticsearch Service for search, I'm going to create usually one index. For something like an e-commerce use case, this would be my product catalog. For CRM, this might be my patients, or might be organized by company or something like that. But generally, I'll have one index in that particular situation. Now, indexes, as I mentioned, are more of a conceptual construct. They're realized by a set of shards. The shards in Elasticsearch are the partitioning of the data within that index. So when I create the index, I specify a primary shard count, and that is how many partitions of data I will have. We could say lots and lots about sizing and capacity planning, but the concept here is that we have a partitioning of the index into shards. Elasticsearch will then distribute the shards for an index across the data nodes in the cluster. Each of those data nodes is going to provide the resources needed to handle indexing, updates, and query requests, and process those requests. So the requests themselves are actually processed at a shard level, even though you reference them by index. When you use Elasticsearch Service for log analytics, you generally are going to use Kibana to access your data and to build visualizations and dashboards. Kibana provides you the means of looking at your data in a nice aggregated way, and especially for log analytics, Elasticsearch Service is very sticky and useful because it gives you the forest view of your log files rather than a tree view. This particular data set is a CloudTrail data set, and you can see I've broken out things like the overall traffic to AWS by region. I've broken out the number of calls. I've looked at the different services, some of the services, and who has been calling them, just to be able to kind of get an overall global view of my AWS usage. Behind the scenes, Kibana is actually making requests to Elasticsearch. We have an example request here. This one is to generate the event sources pie chart. What I'm doing is I'm looking at a particular time slice. Usually, by the way, in Elasticsearch and Kibana, you'll be looking at the last 15 minutes of data. Data itself will kind of, as it ages, it's less valuable. But Elasticsearch is most commonly used for a real-time or near real-time monitoring solution for log analytics. So I have a query that's a time slice, and then I'm aggregating across the event source of the CloudTrail log data in order to generate a histogram of the AWS services that I'm calling. That query goes to Elasticsearch. It gets distributed to the indexes that are relevant for that query, and that query goes to the nodes. The shards process the request, and it comes back. Kibana is a thin web client. It's really just going to format the Elasticsearch response as a visualization. So aggregations themselves are quite a powerful tool with Elasticsearch. As I am using it, I can both filter down my data, so I can issue a query like host is 199, 120 star or burger star. I have an example Apache weblog here, which is a NASA public data set of Apache weblogs from a long time ago, July 1995. But it serves as a useful tool for illustrative purposes. So anyway, I can filter And I formatted it as a table so that you can see the log lines and the various fields in there. I can filter down to particular sets of those log lines. And then my aggregation is simply going to go column-wise, and we can perform various operations. In this case, we can get a histogram of the different values for the status field. I can also do numeric operations like sum, min, max, average. In this case, I'm summing up the bytes column. I can also bucket by terms, and that gives me a distribution of which of the words are being accessed. In this case, which URLs people are accessing. So that's our basics of Elasticsearch. And now we're going to talk about usage patterns. Again, building towards the situations in which cross-cluster search itself is going to be a valuable tool. Monolithic workloads are workloads in which I'm sending all of my data, and I'm using that data for a single group or a single, basically a single tenant is in Elasticsearch. We have some various log ingestion flows here, just to give you an idea. So I have my producers that are generating things like applications or infrastructure logs, security logs, AWS service logs, trace data. All these various kinds of log information are generated on a set of either hosts or AWS services. I need to collect all of that information, and there are various different ways that I can do this. I have Kinesis Agent or CloudWatch Agent if I'm forwarding to Kinesis or CloudWatch. I have various open source tools like Elastic Beats or FluentBit or FluentD. All of these can pick up log lines from my log files and forward them. Then I need to aggregate and transform that data in order to send it to Elasticsearch. Remember, Elasticsearch works with JSON. All of these log files are generating strings. So something has to transform that data into JSON. And at the same time, in order to reduce the total concurrency, I want to be able to aggregate that data and build batches that I send to Elasticsearch. Some of the choices for aggregators and transformers, we have Kinesis Data Firehose. This provides a lot of nice features that make it very easy to deliver log data to Amazon Elasticsearch Service, including error handling, dead letter queues, inline transformations with Lambda, and storing off all of your source data to S3. We also see Kafka used very commonly as either an open source or the managed service in order to bring that data in, buffer it, aggregate it, transform it, and ship it. Amazon S3 actually is also another tool that people use to deliver the log data, and you use it kind of as a queue almost. You generate a lot of data, you push a file into S3, and then you work off of the create event to process and send that data to Amazon Elasticsearch Service. And the last option that I detail here is Logstash. Logstash is, again, an open source technology that we talked about as part of the Elasticsearch Logstash Kibana trio. Logstash buffers and transforms and delivers data to Elasticsearch. When the data is in Elasticsearch, then we have Kibana as a front end to access that data, query it, visualize it, do all that stuff. So a little bit of details on these. Again, I mentioned the S3 Lambda route. This is a low-cost route, but it does tend to incur quite a bit in terms of latency. Still worth exploring. Again, I generate files. Either these are straight up log files, or somehow I've collected these and aggregated them into some set of log lines. I'm going to push those into S3. The object gets created. I'm going to generate an S3 event, and then Lambda will pick that up, go get the file, and push to Elasticsearch Service. Another option is the Redis and Logstash option. Logstash actually is quite rich in terms of the connectors that it provides. It can connect to many different technologies, including Redis, including Kinesis data streams, including all kinds of backends, Kafka as well. So Logstash makes it easy for me to connect to Redis. I can use Elastic Beats to pick up log files from EC2, push them into Redis. Here I'm using Redis more as a buffer than a cache, and then Logstash can pull them from there and push to Elasticsearch Service. Also, there are a number of managed services options. We have EC2 with perhaps Kinesis Agent or Beats or any of the other methods that can pick up log files line by line, ship them off to either managed streaming for Kafka, Kinesis data streams, Kinesis data firehose, EMR with Spark streaming. All of these can buffer and provide the means of accessing that, or provide the means of buffering that data for delivery. We're going to look at Logstash on EC2 as a potential means of reading out of those, or Lambda itself is also commonly used with all of these for shipping the data to Elasticsearch. So in most of these cases, and when we have a monolithic workload, this is really more pointing at the usage pattern is such that I have a single group that is perhaps delivering some application. They have a set of log files that they're generating, and all of those log files are going to Elasticsearch in order to be, in order for them to access it through Kibana. And it's just a single group that is using Elasticsearch. So essentially, we're talking about a single tenant here. And that is in contrast to a centralized workload. So a centralized workload is something that we see quite frequently in larger companies where you have many of these monolithic workloads. And then eventually there's a move to centralize all of that information. There are a lot of reasons why you would centralize that. We'll get into some of those later, but cost and the ability to leverage a single IT department in order to manage things better is generally where that comes from. Now, in this case, we have a number of different applications built by a number of different teams within an organization, and all of those applications are generating data and sending it to Elasticsearch. And the real question is often, how do I handle the tenancy of this situation? Because as I push data into Elasticsearch and as I generate more and more indexes, Elasticsearch actually works harder to support that workload. There are a number of different ways to support this multi-tenant kind of situation. The first of those we have is a siloed strategy, where essentially it harks back to the monolithic strategy. You deploy each of these tenants into their own Amazon Elasticsearch Service domain. That way you retain the separation of all of these things, and they don't interfere with one another when you're trying to scale for them. There's also the pooled or hybrid strategy. In this strategy, you're going to pool together multiples of the tenants into a single Amazon ES domain, and possibly you'll have some siloing as well, where you have larger tenants split off into their own domain. But the general idea here is we're going to pool tenants together and support them in a single domain. And then you have a bridge strategy where you have some tenants and the actual tenancy model itself is implemented below the covers within Elasticsearch. As you push more and more tenants into a single Amazon ES domain, you start to stress the underlying critical domain resources. Some of the things that get stressed are storage. So when you have tenants that have very different storage footprints, you can see clusters get very unbalanced in the usage of storage. And you can find yourself running out of space on some nodes when you still have space on other nodes. And so you want to really be careful about how the storage is actually being used. And really that comes down to the tenancy, because different tenants have different sets of shards, and those shards are distributed unequally, potentially, across the set of data nodes. So it's important that the tenants themselves be fairly close in size, or that you have a strategy for building indexes that are fairly close in size. A similar thing happens with compute. When you send queries or when you send indexing requests to Elasticsearch, those requests multiply over the shards in the indexes that are accessed. And again, when you have a multi-tenant situation, you'll often see unequal usage of the underlying resources just based on the fact of the difference in sizing between those tenants. RAM and networking, similar problem. The JVM heap is half of the RAM, up to 31.5 gigabytes. Again, if you have very large tenants or tenants of different sizes or workloads of different sizes, you can see the JVM usage unequally distributed, and it can be difficult to scale correctly. Networking, Elasticsearch, again, as a distributed database, it relies on networking to be able to send requests out across the cluster and be able to process those requests. So as you add more tenancy, again, you stress your networking. And really, single domain multi-tenancy drives the most in terms of unbalanced resource usage. When you're trying to scale a single cluster to handle tens or hundreds or maybe even thousands of tenants, it's very difficult when there's a large disparity in the usage from each of those tenants. And in fact, underlying the different workloads need different scale, right? So we have a somewhat visualization here where we have two workloads that are similarly sized and one workload that is extra large in comparison. And how that distributes across the shards in the cluster is really not going to be even. So if you can move into some kind of siloed deployment, then that's going to allow you to optimize the scale of each of the workloads. Generally, we talk about this hybrid and siloed strategy where it's okay really to put tenants that are the same size into the same cluster, but where you have large differences in scale, it's important to split the larger tenants out and be able to handle them in their own cluster. But now we have a problem, because we may need to access all of this data together, but we've been driven to some kind of siloed strategy. And we need a way to be able to handle all of this data and yet be able to scale it independently. Another thing that can force you into a more siloed strategy is data segregation requirements. So depending on the type of data that you're working with, often in search workloads, and depending on the local laws, you may be required to keep that data segregated between tenants. Healthcare is a common place where this would occur, where data can't commingle between different tenants. In which case, again, you need some kind of siloed strategy so that you can completely isolate that data. And yet, you may need to search all of that data in some way, shape, or form. And the last thing we'll talk about is blast radius. So when you have a single domain, single cluster with all of your tenants in it, your blast radius for one tenant going down is everybody. And so for the purposes of scale, and especially with a high tenancy count, you may want to decompose the workload across more than one cluster, just so that either one cluster is, because one cluster is too large, or It gives you a way to reduce the blast radius so that one tenant going down can only affect 1/n of your overall workload. You'll still do routing of the tenant-based queries to the particular domains that contain the data for those tenants. But at the same time, you may have cross-tenant queries that you need to handle. And so you need a way both to segregate out or pod out these workloads. As well, you need to be able to query across the whole thing. This is really commonly seen in SaaS applications where you may have hundreds or thousands of tenants and you want to be able to scale freely and you want to be able to grow out to an extremely large size, but you may not be there yet, and also you want to be able to maintain this kind of blast radius and pod the entire workload across multiple clusters. So when you use cross-cluster search with Amazon Elasticsearch Service, and again, this is in the context of these kind of siloing needs, you're going to create a cross-cluster connection between a source domain and a destination domain. That cross-cluster connection will support searching from the source across indexes in the destination. And just in terms of setup, we're going to create an outbound connection from the source domain. On the destination domain, we'll receive an inbound connection request, which we must accept and acknowledge in order to enable the cross-cluster communication. And then that acknowledgement comes out and the outbound connection on the source domain becomes active. This works within a single account, as well it works across account. However, it only works within a single region. I'll review the limits of the feature in just a moment. Once you have that connection established, you'll give it a name, and you can use that name to qualify an index name in order to send a query to the destination domain and the index in the destination domain. You can do the same thing in Kibana. So Kibana will allow you to create an index pattern using this qualified index syntax. And you can query both local and remote indexes together. So you can get from a local index as well as an alias : remote index, and you can search against that data. Access control would seem a little bit tricky, but actually it's pretty straightforward. Traffic, first of all, must have access to the VPC. So if you've deployed your Amazon Elasticsearch Service domain in a VPC, the traffic itself has to be able to get to your endpoint. And the security group here is the way that you can intervene to limit the interaction in the traffic. Once the traffic reaches the endpoint, then we're going to employ IAM policies, or you're going to employ IAM policies to limit who has access to that particular source domain. The identified entity, so if you're with IAM, either you're going to have an open access policy or you're going to have a role or user-based user policy principle. The request itself must be SIG-v4 signed, and that gives an identity that comes along with the query. In order for that query to be accepted once it hits the endpoint, your policy must allow ES HTTP GET for that particular IAM user or role, or there has to be an open access policy. Then within the Elasticsearch Service domain, the Open Distro Security setup, the fine-grained access control, will take the identity that's provided with the request and validate it against its own internal user database. Whether it's IAM or HTTP auth, that's going to provide an identity that will allow you to map particular roles with different actions that are permitted for those roles onto that traffic. The identity itself has to have access to either read or search on any local indices for the source domain. When the source domain forwards the request, the query, to the destination domain, first of all, it's going to hit IAM again. The remote cluster has to have ES cross cluster get allowed, again, or an open access policy in order to accept that traffic. The identity in the destination domain remains the same. If I've used SIG-v4 signing for this request, that provides me an identity. If I've used HTTP auth, that also provides me an identity. So just like with the source domain, in the destination domain, that identity must have the access permissions that allow it to run the query. So the authentication then is evaluated on the destination domain according to the destination domain's policies. And access is granted based on its settings. So we'll talk a little bit about the sort of limits and boundaries of cross-cluster search. You can enable cross-cluster search on an Amazon Elasticsearch Service domain that has been created after the launch date. That is late June this year. And any domain created after launch is eligible for cross-cluster search, provided it is version 6.7 or beyond. At the moment, the cross-cluster search feature only works within a single region. You can't use cross-cluster search to connect domains in different AWS regions. We have a maximum of 20 connections per domain. And when you're connecting two domains, they either have to be the same major version, in other words, both 7.x, or it has to be the latest version prior, so in this case would be 6.8, and any version of 7. So we're going to switch over now for a quick demo and have a look at the cross-cluster search feature. So I've created some domains here in order to experiment and play with, and in particular, we're going to look at our sample data provided through Kibana. We have a couple of different kinds of sample data. There's e-commerce data and logs data. These domains are Elasticsearch Service domains supporting Elasticsearch version 7.7, and I am going to walk through how we connect them. We'll start with e-commerce. That will be our source domain. I go to that domain's dashboard and I open the cross-cluster search connections tab. And you'll see here that I have a point for outbound cluster connections and a place for inbound cluster connections. In this case, I'm going to look at my e-commerce data, and then I'm also going to be able to pull in log data to visualize. So I am going to issue an outbound connection from my sample e-commerce. I have to give it an alias, and remember that I'm going to use this alias to qualify my index name, so it should be somewhat obvious. Let's use sample logs. That's the name of the logs domain. Also, it will be our connection alias. I'm going to connect to a cluster in the same AWS account, and I have a dropdown that lets me choose my sample logs domain. So I'm going to submit that. Now, you'll see that this goes into a validating status. As I mentioned, we create the outbound cluster connection here, we then must go to the destination domain and accept that connection. So let's go to the sample logs domain, and we'll go to our cross-cluster search connections. And you'll see that we have this sample ecom. Let's accept that. And we can review the source. In this case, it is this particular domain. Okay, we have now accepted that, so you can see that we have approved here this connection. I can go back to my sample ecom domain, and you'll see I now have an outbound connection to sample logs. So that's the setup. This is, really straightforward. Easy to set up. Let's have a quick look at our sample e-commerce domain, and let us go and look at Kibana for this domain. All right. Nobody look at my password while I type. So here we have our Kibana e-commerce sample data. I'm just going to quick go over to my development tools tab, and I'm going to have a quick search. And you'll see we have actually a bunch of indexes. Let's search in our Kibana sample data. And you can see here we have a number of documents with currency, customer names, customer genders, order dates, products ordered, including discounts and prices, SKUs, numbers sold, etc. This is our local data. If I were running a search application, I would be issuing queries against this data. Now, I also want to be able to potentially visualize log data that is happening against this. This sample data isn't necessarily going to show that, but I will show you how to connect to from Kibana to the destination domain. So the first thing we need to do is we need to go to our settings and create an index pattern. Kibana uses index patterns in order for you to tell it where the data is, where's the timestamp, so that Kibana can work with that data. So we're going to create an index pattern. You'll notice we already had one for the e-commerce data. So here I'm going to use sample logs colon Kibana sample data logs. So you see, again, this setup is very straightforward. I am able to use my connection alias colon index name, and that enables Kibana to see that destination index. When we work with Kibana, we need to specify the time field so that Kibana can build its visualizations. In this case, I'm going to use the timestamp field, and I'm going to create an index pattern. Okay, now that I have this index pattern, I can go and create a visualization on that data. Well, let's have a quick look at the fields that are in this data. So the log data is essentially Apache Weblog data. We have an agent keyword, the bytes for the request, the client IP address. We have the event itself. I don't know what extension is, geo coordinates. We have a host. We have an index. We have an IP. We have memory, message, refer. All of these are kind of common things. I assume we have a status code, request, response, tags, URL, key, timestamp, etc. So this is all of the data that is residing in the remote cluster that I'm accessing via cross-cluster search. Now that I've created that, let's go ahead and create a visualization. And we're going to look at a simple line chart against Kibana sample data e-commerce. Nope, sorry. We're going to look at a simple line chart against our sample logs Kibana sample data. I got that backwards. When I use Kibana, generally, and especially for a line graph, what I want on the x-axis is usually a date histogram. That's going to show me my data over time. Frequently, I'll put something in the y-axis as well. In this case, let's just quick go to date histogram, and let's see how that looks. So we're looking in the last 15 minutes. This data set is canned, so we have to look back in time. Let's look over the last year. over the last year, and then I can zoom the time window in so we just get a little bit tighter on the data itself. All right, so this is August 15th to August 31st, 2020. This is a count of all of the requests. It's a fine graph. However, we might want to have a little bit more detail in there. So why don't we look at, instead of the count of requests, let's look at the sum of the output bytes. So we'll go sum on the y-axis of bytes. And let's update that. So here again, we have a similar looking graph, although again, the y-axis has changed. This is the outbound traffic from our web server in this case. I'm gonna make one other graph just quickly. So let's go look at a visualization that is a bar graph. And we're again gonna look at our sample logs. And in this case, again, let's put a date histogram on the x-axis. And then we're going to actually sub-bucket on the status code. And I have to pick the field. Actually, let's go ahead and look at it on the URL. So we can see a distribution here of the usage of URL. In other words, this is the usage of our website. So in this case, it's, again, Elastic data. This is the artifacts downloads for 6.3.2 of beats and various. Mostly, you can see that the cross-cluster search itself is very responsive. It's easy to use it in Kibana. It's easy to set it up. And it's a good way for you to support the workloads that we talked about. Switching back over to our presentation, let's just wrap up quickly with, this in our talk today, we talked about cross-cluster search and its ability to allow you to send queries to multiple clusters. And this supports high tenancy workloads, enabling you to split out tenants of varying sizes. It also allows you to segregate your data for compliance or other reasons. And it also allows you to build out pods that enable you to reduce the blast radius for issues that may happen with any of your tenants. You can use cross-cluster search on any new domain you created, and I encourage you to go out there and play. Thanks very much for your time and attention.